Yeah, hi. Good afternoon, everyone. So, welcome to another talk by the Society of Physics Sigma Phi. I'm here to introduce the society, but I'm pretty sure you all know about it. So, we are under the Department of Physics in St. Xavier's College, and we conduct a lot of talks, podcasts, magazines, blogs, a lot of physics related stuff in general. But yeah, we are very proud of it, and this is like one of those riveting talks that we conduct so that people get interested in physics and they just see how fun physics can be. So I am really very honored that sir has agreed to come for this talk. And yeah, I welcome you all. I mean, participants would be joining in, but I'm just telling you, you can put in your doubts in the chat box and we'll get back to you. So yeah, I think I'll hand it over to Ria for introduction.
Just a minute. I think Ria has lost her network. She is joining back in a minute.
Yeah. This happens a lot. Every time we are supposed to say something important, someone loses network.
Would be able to sometime meet offline and have
Yes,
the
sir.
that interacting live.
Definitely.
Hello, can you all hear me?
Yes.
Yes.
Good afternoon, everyone. I have the pleasure of introducing Dr. Rakesh Mazumder as today's speaker for this evening. His expertise lies in solar cells and coronal eruptions. Dr. Mazumdar is now working as a postdoctoral research fellow in Aryabhatta Research Institute of Observational Sciences, Nainital, India. He has obtained his PhD in astrophysics from IISA Kolkata and MSc in physics from IIT Madras. Then he worked as a research associate at the Indian Institute of Astrophysics (IIA) in a DST funded project under the BRICS scheme for 1 year. Dear all, please help me welcome our eminent speaker for the day, Dr. Rakesh Mazumdar.
Uh, so thank you, Ria, for a kind introduction. And I want to, before I begin my talk and a journey to the sun with all of you, uh, let me thank this platform, Society of Physics, very good enthusiasts from St. Xavier's College. And I can remember my days of college, and we were as enthusiastic as you are now. But this technical help now, like this online platform and all, helping a lot. And I'm feeling very happy to giving a talk like that, and hope like I was really in our college days this kind of event could not happen due to this technical advancement was not there. But this is uh, I think this is how the physics should be, like not only reading the books but also what is happening around yours and in the astrophysics, be it any branch of physics. So but I'll not talk in my whole talk any other branches of the physics, but I'll be only concentrating of within my expertise. But this is a journey to the sun, and what I do in the solar physics. So what this is a branch of astrophysics, and we look sun as a star. And I'm not sure, and I was not sure how to address this kind of mixed audience, and whether I should go more in basic or whether I should go more in advanced. But it will be a mixture and overview kind of what I do. I'll try to comprehend you and give some idea about it. But any point of time, if you have any doubt, if you have any questions, feel free to stop me and ask any questions. So it will be also helpful for me just to make sure also you are not sleeping. So let's start with this. So you all might be knowing of this solar minimum and solar maximum, though with our naked eyes, we see sun as a kind of to some astrophysics even it's a burning star, but if you don't look at it is a visible wavelength, but in some other wavelength, let's say this is an image of sun in some extreme ultraviolet wavelength, so you see lot of activities happening, though this is a time-lapsed movie, and thanks to now astrophotography, and even with a small phone you can do a lot. So now everybody knows all this jargon of like it's time-lapse movie and all. So this is a long, let's say more like 11 years or 12 years kind of like activity of the sun, and you are seeing within a minute. But again, you appreciate that there are a lot of activity, and I'll show later on also there are not only this kind of long-term activity, there are a lot of short-term activity which we popularly call as jet and those kind of activities. So I'll be try to not to use too many jargons, but sometime if I use any and you don't understand, feel free to ask me. I'll try to like explain wherever I use any jargon, but even if I don't, so just feel free to poke me. So now first I'll talk about the few in general less famous and very interesting activity of the sun, which not only sun does, but in general other similar stars also do, and try to relate the basic physics with it, like why do that happen, and what scientists understand about that, whether scientists fully understood those phenomenon, or there is still something to be discovered, and if it is, then what is that? So first of all, very interesting thing is about the sun is as we have already seen in the first slide itself, that there is a maximum and minimum we call so that is, you can understand something like this activity of the sun is that's peak period, and there are very less activity in some other period. So peak period we will call it maximum of the solar activity, and minimum will be calling as a very less activity. So now if you plot this solar activity, could be any like this sunspot number, or it could be represented by something some other solar features. So you should keep in mind that every like solar feature or any activity of sun mainly governed by the magnetic field, and the reorientation or generation, amplification or reduction of the field that governs what kind of activity sun will do. So magnetic field is the main driver here, and its amplification and other things. So now if you see, if we plot in x-axis time and in y-axis the activity, it could be any like indicator. Here we are doing it with the sunspot, and now also you see that we are plotting the integrated magnetic field over the sun. So now we see there are a correlation, and this time, though this is x-axis time is not like quantitatively not plotted, but it is typically 11-year cycle, and you can also visually see that there is not exactly 11 year, but it could be here and there, few months here and there. So but you can always see that there is exactly correlated with this magnetic field. So what happens is exactly this north pole of the sun, magnetic north pole of the sun, and the magnetic south pole of the sun flips over this 22 years of period. It covers a full cycle in a 22 magnetic full cycle in 22 years period, and flips one north to south in 11 years period. So that's quite interesting. That does not happen usually. In our Earth we do have a magnetic field, but though we understand that it can be some change over a very big period of year, but at least not in the short time scale. We don't see that our magnetic field is changing, but sun do that. But how do sun do that? Like flipping it and maintaining its magnetic field. Sometimes it's amplifying its magnetic field, but then again it is getting reducing. How all this does happen? So the basic physics behind is dynamo, which will come to later, but just to give you a flavor of what kind of interesting activities happens in the sun. So this is one example. Another very famous and newly discovered example of this is called famously magnetic switchback. So you can see in this point there are something is happening. This is a, by the way, movie produced by the data taken from newly launched Parker Solar Probe. So you maybe heard a lot of about this two newly launched satellite, because not only they discovered and they plan to discover a lot of new things, but also they are technically very challenging, going so much closer to sun in case of Parker Solar Probe, and going in a such a tilted angle for solar orbiter like satellite. Those are very challenging technically. So those are technically also engineering point of view and technical point of view there is achievement. But nevertheless, from the scientific point of discovery also, this kind of discovery, for example, there is you heard a lot about in news campfire and all those thing by solar orbiter, and this magnetic switchback, which I want to like point out, because this was a newly phenomenon which was not theoretically predicted. Rather, it was observationally seen as there this kind of S sigmoid or S kind of shape, some twisted shape you can see in the this plasma, and this is going outwards from the sun. But what are they? How does that happen? So there are mainly, I'll just give a brief like idea. They are either scientists also now debating to interpret this, and like from theoretical point of view, like the simulation and explaining all these events, still scientific are not sure what is exactly happening. But there are mostly two theories coming up, which is one is there's reconnection and another is turbulence. So those two are thought of the main reason, any of those. So but still scientific are debating whether this is either like reconnection or it is like turbulence. I'll come more to like what are the turbulence, what are the switch, like what are the reconnection about that. But for time being, you can appreciate this is an interesting event. And again, this kind of structure also governed by nothing but magnetic field, which is concentrated, some plasma is concentrated along the magnetic field, which we call typically plasma frozen. Basically, all this plasma structure you can see here, all those are governed by the where magnetic field is. So wherever you are seeing the plasma field is concentrating, basically the magnetic field line are basically concentrated over there. And the position where you see those kind of twisted kind of structure, basically magnetic field also is getting twisted, and this plasma are just the following magnetic field line. So we'll discuss about it in more details in coming slides. And now, as I was telling, that it was also technically challenging. So you can see solar orbiter is unlike other like satellite, solar satellite you normally like heard about SDO, namely of this NASA, or we are going to launch this Aditya L1, which will be totally Indian satellite sent by ISRO, which will be hopefully launched next year soon. And all those satellites are in the ecliptic plane, more or less. But the solar orbital will go in a very highly tilted angle. But why that is necessary? So basically, those are necessary to measure the magnetic field in the solar poles, in the south pole and north pole, near to, not exactly, because we are not going at the 90-degree tilt angle, but still we are doing much better in terms of line of sight, because if we are in ecliptic, we are very much accurate about the magnetic field which is on the disk of the sun. But we are doing a lot bad in terms of measuring magnetic field in the poles. So that's why it is very much necessary for this kind of mission, which gives a fair knowledge about this magnetic field in the pole of the sun, which is before this solar orbiter, which was completely not there. Either scientists tried to measure it with some indirect method, or they could just infer with lot of large error but in their measurement. So now I guess Yeah, so now let's just before just knowing all this interesting fact about the sun, and I just jumped into very very much good movies about the sun, and very much nice images. Let's come to now some numbers. So what how big is the sun? And in I'll every time I'll try to compare with the earth as a like reference. So you can see it is 109 times this radius is that of the earth. So you can understand how the things will be big in case of if you are talking about some structure in the sun. So that's also a reason that sun is a natural plasma physics laboratory, and you can exploit that in with some satellite data and all, because if you want to do some plasma experiment and in your laboratory, well, you are welcome to do that, and people are doing that, and a lot of nice things also coming up from out of that. But some scale which is will be never attainable in this kind of such a large length scale. So that is why some plasma physics experiment indirectly, though the problem is here the things are not controlled, we are only taking the data whatever the nature or sun is doing, but still this kind of data helps a lot to understand the basic plasma physics. So this is also I wanted to just highlight in terms of the this comparison of the numbers. So, and also you can see other surface area and circumference and all this volume, etc., and you will appreciate in terms of be it mass, be it radius, how how big the sun is. And now you will be also wondering, okay, this is a pretty huge number, I really appreciate and convinced about that, but what about the other stars? Then your sun is a very small star, and why you too excited about the sun? Is it just because I've done a PhD on the solar physics? No, because if you want to do any study of any star, any fancy star which is not maybe in terms of astrophysics as boring star as sun, but if the first point comes to that, you cannot resolve, simply you cannot resolve even if your best telescope what you can do for the sun. So the basic the accurate and basic knowledge you can get with a with a unprecedented scale of accuracy, that only could be done for the sun. So it is a test bed for any new theory. If you are giving for other stars and all similar solar kind of stars, it would be you should first look at the sun. So there's sun is a you can resolve it well, both in the temporal and the spatial time scale. Now also I have quoted some number rotation period. So sun does not show us same phase, so it do also rotation with 28 days periodicity. So we can see back of the sun as well as the front of the sun because it's rotating. But while its front face is coming, some feature is taking away from us. So we can, and that is also problematic, because if we want to track some feature over the sun, that creates the problem. But we'll see later on that how some from technical advancement and stereo satellite kind of satellite helped, even which went all the way in the back to the in that sent back to the sun and sent us photo of the back to the sun. And with the combined data from both this some satellite which is near to the earth and which is all the way going back to the sun, how good science we can extract from this. So all those we'll see. And also I have quoted some number like the age of the sun in terms of sun as a star. So it is 4.6 billion years, and the photosphere, the effective temperature is somewhat this 5700 Kelvin. But however, the coronal temperature you can say huge. So that will be also a a topic we'll discuss about that. In general, from any light source, if you go away, so you should expect that your temperature, if you go away from any source, so your temperature should decrease. That is our normal experience. It should fall down temperature. But in case of sun, we see in the corona, instead of decreasing, corona is the last atmospheric layer of the sun, so it is and photosphere is just a surface layer, so it is increasing, and it is increasing order of the magnitude. So this problem is known as like some of the it is known as coronal heating problem, and it is kept the scientist very much into the dark, and it is also known as a dark matter problem of the solar physics. But to date, scientist has a fair knowledge and idea about why it is happening, and I'll come to it when we'll discuss about the coronal heating. Now let's come to the fundamental of the sun. I understand that a lot of you don't know, so let's try to understand that. So sun is a star, and like many of other star, it has inside it, we'll call this photosphere is the this layer which is the surface of the sun, and then we'll define a few layers inside also, and on the outside of the surface we'll call this atmosphere, and few layer and few jargons. Just I want you to just remember for the rest of the talk. After that you can forget. I don't mind, but because time to time I'll be using this jargon, so better you remember for time being. So from center to this 0.1 unknot, where unknot I am defining as a surface radius of the sun, so that I am defining as a core. So this is I am defining as a core of the sun. Then from 0.1 unknot to this 0.3 unknot, I am defining as a I'm defining as a radiative zone of the sun, and now only I'm not defining its definition is because of some physical significance, because core is the place where all this fusion is happening. So you know there are hydrogen is getting fused to helium, and if you just from the basic knowledge of physics, you know, if you just get the mass of the helium and mass of the two hydrogen, you will be see you are losing some mass, and that mass is basically with Einstein famous relation equal to this lost mass delta m into c square is converting into the energy, and that is source of all energy. And now if you produce the energy, how will propagate through the sun? So that is why this radiative zone name came, because in this layer of the inside this layer of the sun, the energy is getting propagated by this mechanism of radiation. And now this comes the interesting fact that this this after this okay, maybe this numbers is little bit wrong. I just messed up. So this is 0.7, so core is up to 0.3, and this radiative zone is 0. Till 0.3 to 0.7 unknot. And then if you go to 0.7 to 1 unknot, so you get this convection zone. So what happens exactly in this 0.7 unknot? This energy is not anymore transferring through this radiation, but this convection is starting. So this is called just Jeans criteria, where it is energy because of this density, because of this your density change. So basically your del rho del x, so that get and you get this convection starts to happen. So, and this convection you can you wonder that it is the same convection what you see in your teapot. The same convection cells happen. So now your heat is coming from the lower, and what is the energy? The core. The main source of energy is core, this fusion energy that's coming through radiation, and here it's starting the convection, and now the heated material physically is going up and then getting cooled up and coming down. The same thing what happens in your teapot when you're boiling milk or something. And if you just in your tea pot with milk, if you add some tea leaf or something, you can see nice small pattern, so which is convective cells. So those convective cell exactly you see in the solar surface and the photosphere, they are known as these granules pattern. So you see how the physics is interesting, and how this simpler teapot experiment if you can do, and the bigger version of this you can think of happening in the sun. And with this large telescope, with a high resolution telescope, we do see this granular structure. And those is up to this your photosphere, and after that you have layers of the sun. So first atmospheric layer of the sun after photosphere, we call it chromosphere. And chromosphere, up to some certain temperature, if you go away from the photosphere, your temperature slowly decreases, and some point comes where in the chromosphere temperature started increases. And then in the next layer, which is corona of the sun, and it is not that corona we are heavily suffering from, it is solar corona, and this is named long ago. And due to the coronavirus similarity with this coronal structure, helmet and all, they are named as corona. So solar corona is much older, and this is not harmful at all. So now if in the chromosphere is the layer which is just the in between layer, a small layer between chromosphere and corona, there an interesting thing happens, which is known as transition region. And name suggests that some transition is happening both in density and also in terms of temperature. So density falls heavily, a sharp transition, almost delta delta function kind of falls are there, and also the temperature increases sharply. So those is the coronal heating we commonly refer to, that instead of instead of cooling down, it's getting heated. But you should keep in mind that is not getting started only in transition region. That is only sharply happening in the transition region, but that already started in your chromosphere. But why this happens? So those are the remains mystery for a long time. But then solar physicists suggested mainly two kind of heating which is responsible for this. One is known as DC heating, or this is basically a similar kind of DC electricity and AC electricity named after that. So one is called DC heating and one is called AC heating. But you can understand one physical process is mainly, if you just broadly speaking, is reconnection. So reconnection, and another process we call this wave heating. So some wave is propagating, and which is carrying energy. Carrying energy is fine, but you also have to dump this energy. So this wave should propagate up to from the lower photosphere up to the corona, and also should dissipate in the corona. So both should be happening. So those wave is known as there are different kind of wave. It is a normal, we know it's not like a normal matter. It's not all the matter is not in a gaseous or liquid or any phase. It is the fourth state of matter, which is known as plasma, which is very hot and also charged. That's what it's known as plasma, ionized. So now here the plasma supports some kind of wave, which is, again, I'm using some jargons, so which is known as some pure kind of magnetic wave, which is known as, after scientist Alfvén, so Alfvén wave. And there are some other similar to acoustic waves, so it is called magneto-acoustic waves. So don't going much to details about it and much of its mathematics of it, but you can understand mainly the magnetic field is mainly the perturbation is happening in the magnetic field in case of Alfvén wave, and in case of this magneto-acoustic, it is the nature of this wave. Though magnetic field is also there, it's not that only this acoustic in nature, but also it is a compression. Some compression is happening similar to acoustics. So but magnetic field also there. So it's together. That's why we'll call it magneto-acoustic wave. And now reconnection is a very interesting phenomena. So this is the one process of taking energy away from it And obviously there will be some also dissipation mechanism, which I'm not going into much details due to time lag. And now going to another interesting physical phenomena, which is known as reconnection. Reconnection is basically two magnetic field oppositely directed, which is forced to come together due to plasma flow. They don't want to come actually, because you know from your basics knowledge of even class 12 physics that magnetic field line or electric field line in that matter cannot cross each other, right? But if you compress too much with this flow, which is this plasma flow, it will try to come together, but some interesting thing will happen in between. When it's come sufficiently close together, there will be reconfiguration. What do I mean by reconfiguration? That if initial configuration was like that, so let's say this is the one magnetic field and this is the another, this was continuous. Okay, now it will reorient like this. So this will get joined like this, and this magnetic field will join like this. And now this reconfigured magnetic field, if you calculate the total energy, and if you calculate the total energy before this reconfiguration, you'll find you lost a lot of energy. That is the energy basically get as a some material also will be ejected throughout through this process, which we'll call jet, because it will be too much collimated and it will be coming both outward, and there will be some downflow also usually been seen, but we are most interested about the outflow, upflow, which will come as a jet and carry the energy. And also lot of radiation, not only in visible wavelength or extreme ultraviolet wavelength, but also in other range of wavelength of electromagnetic wavelength, so-called radio or other wavelength, also radiation will be seen. So like that, all this so how this energy is coming, what is the source of energy of all this? So this is magnetic field, and this event, all this event together is called flare, which will be maybe heard of. This flare is happening, so which is a kind of burst in the solar surface, or sometime not in the surface, in the chromosphere or somewhere. So this is the burst event, is basic mechanism in reconnection. And what is happening in this burst event? You are getting the energy out in this your outer atmosphere, and if sufficient mass is also get ejected throughout this flare, so some mass we get also out of this even solar atmosphere, it's come all the way to the interplanetary medium, so which is we call as coronal mass ejection. So I have already taken a lot of your like basic class, so to say, to just understand what I'm going to say. So now I hope you understand a little bit about what is if I call some flare is happening, some CME is happening, coronal mass ejection. If I tell it is happening due to reconnection, so I guess you can follow me. So now let's go to then. So this is just already covered, so we'll skip. And this I'll spend a minute or so, because this is the granular structure I was saying you about. And here in the photosphere you see small granular patterns, not so much visible in this kind of images, because it's not a real image, but it's just a cartoon kind of schematic diagram. But in the high resolution real image, this convective cell you will be able to see in a much clearer and much nicer way. And this is the plot I was talking about. So I covered, I was still in a single slide, but I have not used those slides, but maybe it would have been better if I have been used to explain you all this slide. But nevertheless, you just help with me to understand this kind of graph, so which I was talking that time about this transition region. So if you plot the density and temperature, you see the density is falling from all the way from the photosphere, but you see in this is the transition region where it is fall very sharply. And also in the temperature you see this is increasing in height. So here somewhere in the below the chromosphere, you will see that minimum temperature, then it is increasing and increasing, and this is the point transition region. Sharply it's increase, and it goes to million degree Kelvin from this 5000 Kelvin and all. So after 5000 Kelvin, this is also somewhat 10,000 Kelvin it reaches, some the order of the 10,000 Kelvin, and from the order of the 10,000 Kelvin, it reaches order of the magnitude higher. It goes up to this million Kelvin, which is called as a coronal heating. And there's a mechanism behind that we already discussed, right? This one is reconnection and another is wave heating. Now, how do scientists try to see all these events, or try to get data of this event in that sense? Because seeing means only you are restricted to your visible wavelength, not in the other wavelength of the electromagnetic spectrum. But scientists are not satisfied and with only seeing by the eyes. They want to see all throughout the spectrum. But do nature allow that? Well, you are restricted by your ozone layer, and which will not allow any wavelength like X-ray or gamma rays. We are protected by that, but scientists are not happy about it. So what they will do, they will have to like launch the satellite in the upper atmosphere, and thus they will get the X-ray and ultraviolet ray images, which will be revealing a lot about this phenomena I am talking about, reconnection and all this, because those are some of those are observationally seen through this thing, and some of those are only theoretically and by simulation predicted. But to check that, we need to send the satellite, because through from this even very big telescope in your Earth, you will only be covering this visible light and some part of the radio and some part of other this long wavelength, but you will not be able to see this X-ray, ultraviolet ray, or all those wavelength if you don't go above the atmosphere of the Earth. And also another thing you should keep in mind, that if you are in the Earth also, this day-night problem is there, because you can see the sun in the day, but what about the night? Well, scientists also came out not only the solution with the satellite, but they also made some chain which is known as, you can go into the website and see, there is some gong website. If you just type in the Google gong NSO, so you'll find the scientists have installed a chain of telescope in the multiple observing site all over the world, which cover the sun, observing the sun almost like the all day night, because some part it will be day, but other part will be night. But while here will be night, some other part of the world, Earth, it will be observing the sun. But again, you are restricted with your wavelength, and also cloud and all those problems are there. So best thing to do is satellite. But the problem about the satellite is, if something goes wrong, you really have to spend a lot. So also, so the solution is, you do build a lot of like big telescope from the Earth, and also you send some good satellites. So together, that is the new physics and new science community, which is the vision, that together with this ground-based observation we called, with this telescope from the Earth and this space observation, that is the solution. Together observation can only solve and shed light to the new physics of the sun. And now coming to some other scale which I already mentioned. So you can see this is a dark feature in the solar photosphere, which we call sunspot. And why it is dark? Because magnetic field is highly concentrated over there, which is suppressing the flow, the convection flow, all just we discussed about. So this convection flow is suppressed here due to high concentration of magnetic field here. So if it cannot get energy by the convection from the lower, obviously its temperature will be cooler from the other surroundings. So that's why it appears as a dark feature in the sun. And so this sunspot has two feature. One is in the you can also see in with the naked eye. By the way, if it is a very big sunspot, Galileo did that. You should not do that with your naked eye. You should at least wear your filters and all those things. Now with a small telescope, even you can see those kind of big sunspot. And now you can see the scale. So this is just to the scale Earth and Jupiter, and you can see one sunspot. Inside one sunspot, it can swallow a lot of number of Earth. So now maybe I'll be a little hurry up because I have just talking a lot, but not covering much of the slides. But we won't mind, I guess, if we don't able to cover a lot, because the idea and my also intention was just to give an overview, and whatever we can cover is fine, and we can schedule also another like continuation talk, part 2 of this talk, and we can cover a lot. So we'll hurry up a little bit, but not too much, just to cover and finish things. We'll try to see whatever we want to cover, but in a comprehensive way. So this is the images of the sun in the different wavelengths, and the satellite it is taken from is SDO. So Solar Dynamics Observatory by the NASA. It was launched sometime in 2010. It is nothing like spectroscopy or something is there. It is only pure imaging. I hope you know a little bit about this spectroscopy imaging, and I'm not going too much like basic details of that. But you can understand imaging is just to taking in a single broadband kind of filter but in terms of spectroscopy, you are taking like this count of photons in different wavelength windows, and you are scanning in the wavelength. So you are basically plotting lambda versus number of photons counts, and that's we are calling the spectroscopic information, which is nevertheless very important, and other satellite are there to do that. But SDO just focuses about the image. So now SDO are taking images. All these images is this are your temperatures is mentioned, and much temperature is means also this is higher wavelength. So it is going ultraviolet to extreme ultraviolet wavelength, and now going this way you are going less and less temperature, and you simply can roughly understand with this lambda T Rayleigh Jeans criteria that temperature is inversely proportional to lambda and other way around. So now if you are coming in the lower wavelength, means lower temperatures, mean your temperature is reverse. So now you can see that longer wavelength, you can see some other feature you can see, and I have talked about this sunspot, and now we'll come to some other features in the what you can see in this other atmosphere. So this will be all the solar coronal images which you see in extreme ultraviolet and ultraviolet wavelengths, and this is the picture of the chromosphere, and also this corresponds somewhat to the continuous spectrum, or somewhat you can understand vaguely like it's photosphere, so where you can this sunspot. But you can see somewhere in the chromosphere you can see other feature, and here you can see other feature, and in the chromosphere, and here in the corona other feature. But mind that all these features are linked, so we call it coupled through each other. But what do I mean by that, this coupling? And one more thing before I tell you that is there are other two figure I have not explained, which is this AIA is basically the imaging taking. So from this point, this image to the end of this image, all this image are basically with this AIA instrument, which is just taking the images. But this HMI, so this is some jargon, atmospheric imaging assembly. I don't want to bother you with this names and all jargons, but just keep in mind this is taking a pure image, but this HMI again some other instrument on board SDO same satellite is just measuring this the magnetic field. So these three images is from the HMI instrument. This is the continuum, again similar to the intensity images, but this is giving you really the measurement of the magnetic field, and the black is giving you like this negative magnetic field kind of thing, and what mean positive magnetic field, and what do I mean even by positive and negative. That's magnetic field is coming out and going into the sun. And now again, from as I told, that's all this feature or activity in the sun is mainly governed by these magnetic fields. So it is very important to measure the magnetic field. But also I mentioned that we do accurately measure by SD or any other satellite or ground-based observatory the on disk images. When I try to measure the magnetic field in the pole, due to line of sight, because this is almost perpendicular you see, but there are a lot of oblique angle if you try to see in this pole. So that's the error comes in this measurement of the magnetic field in the pole. And that's why this new solar orbiter and all these satellites comes into the picture. Okay, enough about this HMI and magnetic field and imaging. Now come to this coupling, which I was promised you to say. So what is this coupling I was talking about? Is this some magnetic field you can see in the same place you can this sunspot. So basically this high concentration magnetic field area where you can see the sunspot, and I already explained you why they are appeared in the intensity images as a dark. Now similar same places you can see nice this kind of loop, this loop, because you can understand this is a not a like 3D structure and taken in a 2D images, so it will come that it is somewhere here and there, but in the same same point you can see all this loop kind of structure in the corona. So this is something known as also bipolar region. So not too much bother about the jargons, but some positive magnetic field and negative magnetic field, and together as we call it bipole in terms of any other magnetic or electric. So similar in magnetic, one positive and one negative source, so we are calling it a bipole. So this bipolar sunspot region basically is you are seeing in the base, but some magnetic field line is coming out and marching through the chromosphere all to where all up to the corona, and again it is going back all the way through corona chromosphere and again connecting in the photosphere. And those things actually you are seeing those kind of coronal loops in terms of coronal loops here. We call it coronal loops. And there are other structure also called filament and all. I'm not going to in that due to time limit. And now you can see I have just made a collage of this kind of all these images, magnetic field and different wavelength images. And this is nothing to do about great science, but just out of like aesthetic point of view, it looks nice, that's all. And now if you are want to see how this happens both from aesthetic point of view and scientific point of view, now you can see now I'm covering with a nice animation different portion which you see in terms of white light, nothing is there, but when you cover with this other wavelength and look at the sun in the other wavelength, you can see how they are looking. But you must see that sunspot, in case of you do sunspot, you do see a lot of nice kind of loop, which you call that corner loop. In the same place you see them. Okay, so that is the message, and this is the takeaway home knowledge I wanted to give about them. And now, though I'm left with a lot of other things, but I'll, as I told, try to cover how much I can with this time limit in mind. So now if you see the long-term evolution of the sun, you can see in the extreme ultraviolet I'm talking about. So this is sometime in the 1996. So I have already told this 2010 was the images of the extreme ultraviolet taken by your satellite like SDO, but then you will wonder when how these images of 1996 came. So this is another satellite. This is called named Shoho, which was again in some NASA mission, and you can see from all the way 1996. If you come all the way to 2007, so it was a minimum phase, less activity and less stuff was there in the sun. Now you are coming towards the peak period 2001 2002, you see a lot of structure at the sun. Again you are going to some minimum period in 2006 and you cover it in 11 years, and then you are going again to the maximum period. And one minimum to another minimum, in terms of sunspot, it is 11 year, and in terms of full magnetic, it is 22 year. And now let's try to cover a little more. So this is the what I was talking about in another nice representation. So you can see this is the I was talking about this 11-year cycle, and this 22 and 23 is just the number. We have given some old cycle, just number 1, and according to that, every 11 year we just increasing number, and somewhere we are here in after cycle 24, we have just started in 2021 cycle 25. And there was a lot of speculation that cycle after 24, the 25 will be a very weak cycle. It will be a ice age again will come, but with like again proving all this speculation. Not only speculation, there are a lot of simulation and theoretical point of view also was there, but actually nature proved a lot of scientists wrong as well, that it was not even a ice age and not even close to a weakest cycle. It was even it is showing up to be a little stronger than even cycle 24. So you can see scientists knows a lot, but still there is a lot to know. And you guys are young minds, and you are the people which who will contributing, I hope, a lot in those aspects. And now if I just show that in a nice representation. So this is the minimum in 2008. So where you can see sun is doing a lot of less activity, and now you can see in 2012 and 2014, you can see these are the two kind of peak, and there are a lot of physics why it is not a single peak and not a it is a two peaks. I'm not going into that, but again you can see in sometime of 2017 it is started less and less, and this maybe I just forgot to tell you, but when I was talking that in terms of sunspot or other features, it is just as simple as just counting the number of the sunspot. Galileo did that, and even before that Chinese people did that. Just count the number of the sunspot, you take a note and plot it over 11 years, you will get this kind of nice cycle. You plot it over 22 years, you will get 2 cycles like that. And now with this great big telescope and all, we can do even better, right? So now coming to this amplitude variation, not only that it is 11-year cycle, but also you can see this amplitude of the cycle. There is a long-term trend. We see there are even some more like 22-year periodicity or sometimes 30-year periodicity also is being predicted. But this is again not like confirmed due to, because we have roughly have some